Okay, like we said in the last one, we're doing examples. What I want to do in this one, I want to look at a problem where we've got something sitting on a surface like this, and there's two weights on each side of it, right? So, and then they want us to find out what's happening to the system. And remember, they are linked with string, therefore it's a system. Everything's going to do what the other part of the system does. It's not going to be different to it. Okay? So all the accelerations of the individual parts must be the same. Let's just draw it. They've given us a problem which, in essence, is we've got this, let's say, okay, and we've got 10 kilograms over there. We've got this coming here. All right. It's going over a pulley. As I've said before, I'm not an artist. And let's say they say we've got a 5 kilogram weight over here, and we've got a 3 kilogram weight over there. Now, you guys, surely you've seen this kind of problem, right? It could be this, or it could be two boxes sitting on there and one weight. We'll do one of those as well at some stage. Let's have a look and see. What do we do first? We put in FW every single time. So let's put FW over here. This is going to be FW is 49 newtons, and this side they say FW is going to be 29.4 newtons, which is my weights acting. I've got to go up to this guy, and FW here is going to be equal to 98 newtons. The next thing we say is, right, what's holding this up? There's a piece of string there, so that's a T2 that I've called T2. Let's have a look. This one I called a T1. This one I called a T1 as well. Obviously they must be the same. The tension in a piece of string is the same both sides. Right, now the next bit is they said mu is equal to 0.1. They could have said a frictionless surface, but highly unlikely, so they've given us that. Right, now let's look. Where is friction acting? It's acting there. It's not acting here. It's not touching anything on the sides. Friction is on this surface here. Remember, it's where things touch. Okay? Technically, yes, the weight's down. I've got air resistance, but usually they say ignore air resistance. All right? So we've put in FW. Next thing, I'm going to put in F normal. In this case, is going to be 98 newtons like that. And I can calculate FF is equal to 9.8 newtons, 0.1 times 98, right? I probably should have done that, which gives us 9.8 newtons. Okay. Now, here's the trick. We say, right, once again, it always comes down to the question, which way does friction want to act? Ask yourself the problem. Just look at it and say, which way does that 10 kilogram block want to move? We've got 5 pulling down this side of the table, and on the other side of my desk, we've got 3. So logically, the 5 is going to pull the 3, isn't it? So it's going to want to move in the direction like so. Therefore, friction is going to be there, and it's going to be FF equal to 9.8 newtons. Right? You must go and ask yourself that test question. Which way does it want to move? There's not a mathematical answer that's going to give to you. Just have a look at it. Logically, the 5 is more than the 3, therefore it's going to want to pull it off the table, isn't it? Now we can go and we can say, right, okay, let's say, question, let's look at forces pulling off the table. What's the force pulling me off the table? It's 49 newtons, isn't it? So this one here is 49 newtons. Now let's have a look at what's the opposite direction. Forces holding us on the table, right? Well, there's friction, isn't it? plus the 3 kilogram weight, which then means we've got a force of 9.8 newtons, friction, plus 29.4. Let's have a look. 9.8 plus 29.4 is going to be equal to 39.2. Can you see that? Okay. So what have we got? We've got 39.2 newtons, right? That is holding us back, right? It's the friction on this and the weight on the other side. Those are the two forces trying to stop us moving. And the force that is actually causing us to move is going to be our 49. Let's look. Are the forces pulling us off more than the forces holding us on? Well, how do we do that? Pulling off is 49 minus 39.2 newtons. Okay. And have we got an F net? Yep, we have of 9.8. Okay. Why do we say that? Because the force pulling us off is more than the force holding us, so we're going to move. We haven't got enough friction and there's not enough weight on the other side to hold us on the table. It's as simple as that. So F net is going to be 9.8. Therefore, what do we do next? Therefore, we say F net equals MA. So F net is going to be 9.8, is going to be equal to mass. Now let's just stop a second. What mass? It's the mass of the whole system. That's what we're pulling with that force, isn't it? We're not just pulling one of them, we're pulling everything. So we've got to add them, 10 plus 5 plus 8 times A, and we get A to be worked out to, let me just check here, it's going to be 0.544 meters per second squared. And then we say to the right. That's it. What have we done? We found the acceleration of this system. Because there's an F net, and we found it, therefore we can work out MA. The place to be careful is with that mass. Remember, that force that's pulling me down off the table is pulling the mass hanging here, plus this one, plus that one. That force is pulling all the mass. It's the same as a train. The force of the engine is pulling all of the mass of all the coaches with it. And that's the unbalanced force causing the system to move. Now the next part of these problems is then calculate the tension in the cables. Okay. Well, once again, let's go to the left side and we say, what did we have there? We had T1, right? And we had 29.4 down. Remember, this was our 3 kilogram block. Now I always go and I put in my acceleration. I say, you are also accelerating up at 0.544 meters per second squared. That's to remind me. Immediately, I say, right, I've got an acceleration. Now I'm just looking at this block on its own. And I say, F net is equal to MA. F net, in this case, is going to be 3 kilos, can you see it, mass, times 0.544. 3 times 0.544 is 1.632 newtons, right? That's the net force that's accelerating that block up, isn't it? Now, the question we ask ourselves, is T1 bigger than 29.4 or smaller? Well, if it's going up, it must be bigger because it's experiencing a force upwards, isn't it, to move it up. So if T1 is bigger, by how much? It's bigger by that much. So therefore, T1 is going to be equal to 29.4 plus 1.632, which is going to be equal to, I've written it down here, 31.03. Right? Now we go to the opposite side and we look at remember, we've got over here, I'm just going to draw it over there. We said we had T2. Remember, this was our 5 kilo block. Acting down, we had 49 newtons over there. Right? Now what do? We once again, we say, but you're accelerating upwards at 0.544 meters per second squared. Right? Accelerating up? Nope. Accelerating down. It's coming off the table. Right? So every time, ask yourself, put in what is happening into those individual components. Right? It's the same when we get to electric circuits. You put it back in onto your diagram, then you can see what you're doing. Okay? And it's kind of a checklist, if you like. Have I covered everything? Yes, we're going down. Now the next question to ask, well, if we're going down, is the force up bigger or smaller? Well, it means essentially, doesn't it, that I'm not strong enough to hold it. My tension's not enough. It's falling down. So my T2 over there must be less. We always go and we work out F net. Okay, I'm going to go here. Say F net equals MA. F net in this case, M is 5 kilos times my 0.544. So my F net in this case is going to be 2.72 newtons. Right? Now, is it 2.72 more down or more up? Obviously, it must be down. Why? Because that's less, right? So, less by how much? Less by that much. So we say, right, T2 is going to be, T2 is going to be 49 minus 2.72, and that gives us 46.28. Right? So it must be, because my T2 must be less than my weight down, because I'm going downwards. Now, just in sort of, let's put them together. The block in the middle over here is, what did we have? We had our 10 kilo block. So I'm going to put in F and F normal there, which was 98 and 98. Right? I'll just put in the block. This is our 10 kilo. Now we said which way is friction acting. I'll put it in red. Friction we said was 9.8 acting that way. Right? Now, let's just fill it in. What forces are this way? Well, we've got this way, we've got a T2 equal to 46.28. There it is. This way we had a T1, and that was equal to 31.03. Right? Now let's have a look at this block and see if there's an F net on this block. But first we have to say to ourselves, hold on, we're missing something. We haven't yet put in our acceleration, 0.544 meters per second squared, right? All right? That's what's happening. Now this time I'm going to check myself this way. I'm going to say, well, those are the forces I've worked out. So if those are the forces, let me see if there's an F net. So let's say to the right is 46.28. To the left is going to be 9.8 plus 31.03. Let's have a look. 9.8 plus 31.03 is going to be equal to 40.83. So yes, my force to the right is more than my force to the left, so the block will move that way. So it confirms the direction. Now let's say, right, therefore there is an F net, and my F net is going to be minus 46.28 is going to be equal to 5.45 to the right. Okay, 5.45 to the right. Now, The last thing we say is there's an F net. Got it. Let's see. F net is going to be equal to MA. 5.45 must be equal to mass. It's my 10 kilo block. Therefore, A must be equal to 0.545 meters per second squared, meters second squared. And look, that ties up with the 0.544 that we calculated. Therefore, in the third decimal place, right, that's a rounding issue that we've got. Can you see that all we've done is we've taken the 3 blocks, we've looked at it as a system, we've calculated the acceleration of the whole system. In other words, we're ignoring the internal forces of the tension because it doesn't matter, we don't need it. We need the external forces. This is pulling me off the table. What's holding me back? The friction and the 3 kilo on the other side. That's what's keeping me, but it's not enough. So I'm going to go off the table. Okay. What I'm going to do next is do Newton's laws of gravitation, right? Which is in essence a very simple section of the work. But what we've got to do is we've got to go back up to grade 7 or 8. A lot of the questions with Newton's law of gravitation are reflected in ratios. So we're going to have to do a lot of like ratio analysis. The same thing when we get to chemistry. One of the basics of it is going to be working out how many cups of this to how many spoons of that to whatever we want to put in. It's ratios again. So we'll have a look at Newton's laws in the next one, and then we'll do some examples on those.